how is everyone doing today? Are you currently in self-isolation? Remember to stay safe and maintain your health. If you're bored, come study with us. Welcome to Mechanics and Heat Physics class. In this video, we will be discussing about fluid statics or hydrostatics. Do you know how to swim? In order to swim, we need to master some skills in order to not drown when we are in water. How will these skills help prevent us from drowning? When the body enters water, a buoyant force will appear. The more area of the body enters the water, then the bigger the value of the buoyant force will be. That's the basic principle of swimming. Said buoyant force will be what we learn in this opportunity. This video will explain about fluids, density and pressure, fluid at rest, measuring pressure, Pascal's principle, and Archimedes principle. Before we begin, let me introduce the members of our group. This group consists of Anindya Fawwaz, Cornelia Adristi, Nadine Almira, and Shaffa Mutia Z. So, what is a fluid? A fluid is a substance that flows because it cannot withstand shearing stress. It can, however, exert a force in the direction perpendicular to its surface. Matters that count as fluids are liquid and gas matters. In order to understand more, let's begin with discussing fluids, density, and pressure. Do you recall that every object has a different mass density from each other? To find the density of a fluid at any point, we isolate a small volume element of delta V around that point and measure the mass of the fluid contained with that element. Mathematically, density may be written as ρ equals with delta M divided by delta V. Pressure is a force that works perpendicular to a surface and divided by the area of said surface. Mathematically, it is written as P equals with delta F divided with delta A. The international system of units of pressure is Newton per square meter, which is given a special name, the Pascal. Another unit for pressure that is more well known are atm and torr with the equation 1 atm equals with 1.01 micropascal, equals with 760 torr, equals with 14.7 pounds per square. Now, let's move on to fluids at rest. Let's do a force analysis on fluids at rest. Imagine A shows a water tank that is open to the atmosphere. We know that the deeper an object is within the water, the bigger the pressure will be. Said pressure is caused by F1 or downward force is due to the water pressure pushing on the top surface. F2 or upward force is due to the water pressure pushing on the bottom surface and gravity pulls downward on the sample. According to Newton's first law of motion, where sigma F equals with 0, the force applied with F2 equals with F1 plus M multiplied with G. By using the equation P equals with F divided with A on F2 equals with F1 plus M multiplied with G, we can write the formula for pressure difference. When a liquid column is stationary, then the pressure difference between two depths is P2 minus P1 equals with ρ multiplied with gravitation multiplied with Y1 minus Y2. In order to find the pressure of a certain point, we can substitute Y1 equals with 0, P1 equals with P0, and Y2 equals with minus H at the equation to get the pressure at depth H. Then, P equals with P0 plus ρ multiplied with gravitation and multiplied with H.
Then, how do we apply this method of pressure measurement in real life? First, we need to know about the mercury barometer. Mercury barometer is a device used to measure the pressure of the atmosphere. From the name itself, we know that the long glass tube is filled with mercury and inverted with its open end in a dish of mercury, as the figure shows. The space above the mercury column contains only mercury vapor, whose pressure is so small at ordinary temperatures that it can be neglected. The atmosphere pressure can be measured with this device by using the equation PO equal to ρ G H, where PO is the atmosphere pressure, ρ is the density of mercury, G is gravitation, and H is the difference in height between the surface of mercury in the tube with the surface of mercury on the container. The second device is called the open tube manometer. An open tube manometer measures the gauge pressure of a gas. It consists of a U-tube containing a liquid, with one end of the tube connected to the vessel whose gas pressure we wish to measure, and the other end open to the atmosphere. Pressure on the gas inside the tank can be measured with Pg equal to P min PO equal to rho GH, where Pg is gas pressure, rho is liquid density, G is gravity, and H is difference in height between the two tips of the liquid inside the tube. The gauge pressure can be positive or negative, depending on whether P more than PO or P weaker than PO. Now we will discuss about Pascal's principle. Pascal's principle states that a change in the pressure applied to an enclosed incompressible fluid is transmitted undiminished to every portion of the fluid and to the walls of its container. For further explanation, please observe the following illustration. According to the image, the atmosphere, container, and shot expert pressure, or which can be written as Px on the piston and thus on the liquid, the pressure at any point P in the liquid is then P equal to Px plus rho GH. When we add a little more lead shot to the container, the quantities R, G, and H and are unchanged. So the pressure change at P is delta P equal to delta Px. Based on the formula that apply, this pressure change is independent of H, so it must hold for all points within the liquid as Pascal's principle states. To understand more about Pascal's principle, let's discuss about Pascal's principle and hydraulic lever. How does hydraulic lever work? The hydraulic lever is shaped as seen in the shown. The force applied on the left and the downward force from the load on the right produce a change in the pressure of the liquid that is given by delta P equal to Fi per Ai equal to Fo per Ao. Based on that formula, then we can assume that Fo equal to FiAO per Ai. If we move the input piston downward a distance, or we can write it di, the output piston moves upward a distance, or we can write it do, such that the same volume of the incompressible liquid is displaced at both pistons. Then volume equal to AIDI equal to AODO, which we can write as DO equal to DI per AO. From the equation above, we can write the output work as work equal to FODO equal to FIAO per AI, DIAI per AO equal to FIDI.
After getting to know about Pascal's principle, we move on to Archimedes' principle that applies to hydrostatics. Archimedes' principle states that when a body is fully or partially submerged in a fluid, a buoyant force from the surrounding fluid acts on the body. The force is directed upward and has a magnitude equal to the weight of the fluid that has been displaced by the body. We can conclude that the buoyant force on the body is equal to the mass of the fluid that is displaced by the body times gravity. For example, if we put a piece of rock on water, said rock will sink. Meanwhile, if we do the same with a piece of wood, it'll float on the water. Image A explains that the buoyant force is due to the pressure of the surrounding water. Image B shows that the net force is downward, so the stone accelerates downward. And image C shows that the net force is upwards, so the wood accelerates upwards. When a body floats in a fluid, the magnitude of the buoyant force is equal to the magnitude of the gravitational force on the body. We can write this statement as Fb equals to Fg. Since we know that Fb equals to the displaced mass times gravity, we can write this as Fg equals to the displaced mass times gravity. In other words, a floating body displaces its own weight of fluid. Placing a stone on a calibrated scale gives us its weight. However, if done underwater, the upward buoyant force on the stone decreases the reading. This reading is then called the apparent weight. The apparent weight is equal to the actual weight minus the magnitude of the buoyant force. To understand more, let's try to solve some problems relating to hydrostatics. First problem, find the pressure increase in the fluid in a syringe when a nurse applies a force of 42 Newton to the syringe circular piston which has a radius of 1.1 cm. Now we know that F equals to 42 Newton and R equals to 1.1 cm. We know that the change in pressure is caused by the force applied by the nurse. Therefore, we can find the pressure difference with the equation delta P equals to F per A, where A is the surface area of the syringe, which is circular. Now, with some calculations, we obtain the pressure difference 1.1 times 10 to the power of 5 Pascal. Next problem. The plastic tube has a cross-sectional area of 5 cm squared. The tube is filled with water until the short arm of length 0.8 meters is full. Then the short arm is sealed and more water is gradually poured into the long arm. If the seal will pop off when the force on it exceeds 9.8 Newton, what total height of the water in the long arm will put the seal on the verge of popping? Based on Pascal's principle, the weight of liquid on the left side is equal to the upward force on the right side, because the pressure is constant among the liquid. Now with some substitutions, we obtain that the force equals to weight. Since weight equals density times volume times gravity, which is equal to the popping force of 9.8 Newton, we do some calculations to obtain a height of 2 meters. And since we have the initial length of short arm, which is 0.8 meters, we add these up to get a total height of 2.8 meters.
The third problem will be about measuring pressure. In one observation, the column in a mercury barometer has a measured height of 740.35 millimeters. The temperature is -5 degrees Celsius, at which temperature the density of mercury is 1.3608 times 10 to the power of 4 kilograms per meters cube. The freefall acceleration at the site of the barometer is 9.7835 meters per second square. What is the atmospheric pressure at that site in pascals and in torr? From the problem, we know that height equals to 740.35 millimeters and the density is equal to 1.3608 times 10 to the power of 4 kilograms per meters cube. Therefore, with the equation pressure equals to density times gravity times height, put in the known information which has been converted to its respective international systems of units. We have pressure equals to 13,608 times 740.35 times 10 to the power of -3 times 9.7835. And then we will have pressure equals to 98,565.66 Pascal. From that, we can find the pressure in torr with the equation P torr equals to P Pascal over 133.33. We have P torr equals to 98,565.66 over 133.33, and then in the end we receive P torr equals to 739.26 torr. The fourth problem is about Pascal's principle. A piston of cross-sectional area A is used in a hydraulic press to exert a small force of magnitude on the enclosed liquid. A connecting pipe leads to a larger piston of cross-sectional area A. A. What force magnitude will the larger piston sustain without moving? B. If the piston diameters are 30.8 centimeters and 53 centimeters, what force magnitude on the small piston will balance a 20 kilonewton force on the larger piston? For point A, As per Pascal's principle, a change in pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and to the walls of the containing vessel. The pressure at the small piston is equal to the pressure at the larger piston. The force of the small piston over the area of the small piston is equal to the force of the large piston over the area of the large piston. Therefore, the force of the large piston will be equal to the force of the small piston times the area of the large piston divided by the area of the small piston. For point B, we can use the same method used in point A. From the equation received from point A, we know that the force of the small piston will be equal to the force of the large piston times the area of the small piston divided by the area of the large piston. Convert the known information into its international system of units and put it inside the equation previously mentioned to form F equals to 20,000 times pi times 0.038 square over 4 divided by pi times 0.53 square over 4. And then we will have, therefore the force of the small piston will be 102.8 newtons. Lastly, problem 5 will discuss about Archimedes' principle. A cube of edge with a length of 0.6 meters and a mass of 450 kilograms is suspended by a rope in an open tank of liquid of density 1030 kilograms per meter cube. Find A. The magnitude of the total downward force on the top of the cube from the liquid and the atmosphere, assuming atmospheric pressure is 1 atmosphere. B. The magnitude of the total upward force on the bottom of the cube. C. The tension in the rope. And D. Calculate the magnitude of the buoyant force on the cube using Archimedes' principle. What relation exists among all these quantities? To make things easier, it is better to draw the diagram of the force and pressure that happens in this problem. First, we discuss about point A. Here we are asked to find the force experienced on the top of the cube. To find it, we can use the equation force equals to pressure times area. As you can see, the force that affects the top of the cube is the atmosphere pressure and the water pressure on top of said cube. Therefore, the force can be found by adding the two pressures mentioned previously. With that, we know that the formula used will be force on the top equals to pressure of the atmosphere plus pressure on the top times area. Water that press onto the cube from the top will have the same area as the one on this as the one side of the cube. Therefore, A can be said to be L square. As for the pressure from the top of the cube, it can be written as density times gravity times height. Afterwards, we receive the equation F top equals to P atmosphere plus rho times G times L over 2 times L square. With that known, all we need to do is to input the known information to form F top equals to 101,300 plus 1030 times 9.8 times 0.6 over 2 times 0.6 square and then from that we know that the force on the top of the cube is 37,558.15 newtons. Point B asks for the force experienced by the cube from below. The formula will be the same as point A, with the difference being pressure on the top replaced with pressure on the bottom. Based on that, we get F bottom equals to P atmosphere plus P bottom times A. F bottom equals to P atmosphere times rho times G times 3L over 2 times L square. F bottom equals to 101,300 plus 1030 times 9.8 times 3 times 0.6 over 2 times 0.6 square. Therefore, the force on the bottom of the cube will be 39,738.46 newtons. Point C asks for the tension that is experienced by the rope. Since the cube is static equilibrium, the total of Fy equals to 0. Input all the force on the y-axis according to their respective directions. It can be written as T minus F top minus W plus F bottom equals to 0. Because we are looking for the tension on the rope, then it will be easier to move all the other components to the other side of the equal sign. So we have T equals to F top plus W minus F bottom. With that, all we have to do is put in all the necessary numbers. So, T equals to 37,558.15 plus 450 times 9.8 minus 39,738.46. Then finally we will find that the tension on the rope is 2,229.69 newtons. For the last point D, we are asked to count the buoyant force. We only need to input numbers according to the formula. So FB equals to rho times L cubed times G. FB equals to 1030 times 0.6 cubed times 9.8. With that, we will receive the result that the buoyant force is 2,180.3 newtons. That's all the materials we bring regarding hydrostatics. These materials were obtained based on the books Fundamentals of Physics 10th edition, Modern Technical Physics 6th edition, and the website study.com. Thank you very much for tuning in to our video on mechanics and heat physics class. We hope you understood things to heart. Stay safe and stay at home.